Gravitational potential energy is defined, I'm going to use the definition, it's the work done by the net force to displace an object against gravity. Okay, that is the work done against gravity, the work done against the gravitational force. That's the work done as we lift an object from some fixed reference point to whatever position it's at. Whatever position it's at, it has a potential energy that's equal to the work done to displace against gravity from the reference point to that position. Maybe a better definition logically would have been to say that gravitational potential energy is the work done by gravity as an object falls freely from one position to another, to a reference position, from our position to a reference position. But I like to connect this with thinking of the work that we have to do rather than thinking about the work that gravity does, which is a little more abstract. The work that we do is more tangible to us, and then we can understand that gravity does equal an opposite work in accelerating the object back down to the reference point. So, as an example, if we raise a 100 kilogram mass, a vertical distance of 50 meters, how much work does that require? Well, work is force times distance. How much force do we have to exert against gravity? Well, the weight of the object, 100 kilograms times 9.8 meters per second squared, or 980 newtons against gravity. So that our potential energy change is equal to the work done between the 2 points, which is going to be force times distance, 980 newtons times 50 meters, or 49,000 joules. Our units are those of Newton meters, which are joules, and we write that as kilogram meters squared per second squared in what's by now a familiar conversion. Elastic potential energy, we're going to say, is the work required to stretch an object from equilibrium to given position. Now, maybe a little ambiguous about object. We have a mass, and we have something like a spring or a rubber band, or the tension in a pendulum, or as we've seen, the buoyant force of water on a uniform cylinder bobbing up and down in the water. All of these give us something that's very much like elastic potential energy. I guess the water isn't elastic, and the tension in the spring really isn't elastic, or the tension in a string of a pendulum, although it arises from elasticity, the force is really a component of a constant elastic force, and the component changes. Anyhow, enough digression. Now, again, it's a potential energy to stretch the spring or whatever it is from equilibrium to a given position. So if we have a spring, now a spring has a force constant, which is a number of newtons per meter that we experience as we stretch it. If we stretch the spring a meter, we get 1,000 Newton force. We stretch it 1/100 of a meter, we get 1/100 of that, or a 10 Newton force. Then from its equilibrium point, at x equals 0 to x equals 3, if we have this force constant, at 3 meters, we have 3,000 newtons of force. So we take the average of the two forces, 0 at equilibrium and 3,000 newtons at the 3 meter point, and we get 1,500 newtons. So our potential energy change is the amount of work done between the 2 points. 1,500 newtons by times 3 meters is 4,500 newtons. Now, of course, what we've done here is essentially the same as the derivation of the fact that the change in potential energy is 1/2 kx squared. This is the average force 1/2 kx between 0 and position x times the distance x, and that gives us another calculation that comes out with the same result. And our units are units of kx squared. K is measured in newtons per meter, which we multiply by meters squared to get newtons times meters, and that's joules, which is kilogram meters squared per second squared, and so on. And we're used to that idea. Okay. Impulse. What's impulse? Impulse is the product of an average force and the time through which that average force is applied. For example, if a golf ball collides with somebody's skull, and that usually does only painful but not serious damage, although it can be serious, we get an average force of 2,000 newtons possibly. That's a lot of force. Actually, it's not all that much force for a golf ball collision, and your skull can easily withstand that kind of force, although it does raise a lump, for a very short duration, 5 milliseconds. Okay? Now, a 2,000 newton force acting for 5 milliseconds gives you an impulse of 2,000 newtons times 5 milliseconds, or 10 newton seconds, which is 10 kilogram meters per second. And that's the impulse of the force. Now we observe that the impulse is going to be equal to the change in momentum of the skull, assuming that the skull isn't attached to something else like the rest of somebody's body. And of course we don't really want to assume that. We don't even want to think about that. The units here are units of Newton seconds, which are kilogram meters per second. We note that those are units of momentum. And that makes everything consistent with what we're going to look at next, which is the fact that the momentum mv is what changes as a result of the impulse. And it's conserved in a closed system, we've seen, because all impulses happen in equal and opposite pairs, leading to the idea of conservation of momentum, or the law of conservation of momentum, or the momentum theorem, whatever you want to call it. Depends on how you think about it. An example, the skull that we just saw in the preceding example, let's say that skull is disembodied, let's say the person's dead, mass of 6 kilograms, which is a pretty thick skull, maybe thinking about still being a brain in it, so that m delta v is 10 kilogram meters per second, and we can easily determine the delta v from this. And that might be a typical example. And of course we still have units of kilogram meters per second.